Dear students, last class we discussed the gradient and use of these concepts to find out the edges in the images. So we saw the gradient and we discussed that it's based on the concepts of the derivatives. So we saw these things and the direction and the strength of the uh, gradient, and then we discussed that all these things, all of them, and this was the example we saw for the zebra. For example, over here we have got this gradient that is finding the change in the x direction. And how I can know that this is change in x direction? Because when you move in the x direction, you see that the changes over here are clearly visible, these lines. Whereas you are moving in x direction and these changes are a little bit ignored. And this was more clear when we did in the lab the example of those chess boards. So we saw these things. So this is the example, another one for this tiger. This is the x change and this is the y direction change. So we did this, and this is one example of some filter that is used. So we use filters for gradients or the derivatives, and the one that's popularly used is the Sobel. So we used it for Sx and Sy. So let's come now to the left side. So here, if you remember, so this was the template part. Here we have got this how to implement this Sobel operator. So first of all, what we do is that you have to implement a kernel that represents the Sobel. So remember, there are Sobel x and y. So gradients are implemented separately for x and y directions. This one over here is for x direction. So you see it has got the values that are changing when you move in the x direction. That's why it's x. So you have these minus coefficient values, and then there is zero, column of zeros, and then there is a column of positive values. So this is same thing, the one that you see here, it's the same that's in the slides, this one. So x is shown to you over here, and what about the y? Y is given below. So what they did over here, they implement the sx. After this, we read the image from our image sources. The image we use is the chessboard1.jpg, and we read it as a grayscale image. And what we try to do is that, so this figure command is just to reset the size that we want. You can make it larger, and then you display the original image. So I'm sure with the grayscale CMap, this is the original image. And now here is the step where we implement this thing over here. So we apply on the chess1 image, we apply the SX kernel. So SX is because SX is for the derivative. So what we get is we will get a result which will be in the edge detection. So the result will be the edges inside this image. So here you see the edges that are shown, they are only the edges that can be seen when we move in the x direction. Clear? Similarly, the same thing happens for the y direction. If you see the kernel that's representing the y direction, it is in a shape such that moving in the y direction from below to up, you will see first of all a row of negative values, then a row of zeros, and then there is a row of positive values. Again, same things are happening. We applied the filter 2D command, which is used to apply this kernel on the image, and this is the result you see over here. This time you will only see those changes that are occurring in the y direction. Clear? I hope it's quite clear. And now this is your task. I will check at the end, or maybe after a week I will tell you how to submit it to me. The task is that the Sobel operator is implemented. You have to implement the other two also. Prewitt robots, you have to implement it on the same image, or else let's change the image. So the images, let me check. So the chessboard is given, this one. So I have only one chessboard that's in this direction, chessboard 1. So okay, so for this chessboard 1, we will be you will be implementing the two kernels, the Prewitt and the robots, and this you will show in the same page over there for the lab Jupyter notebook. Just below this thing, add cells over here, and you will implement these two things. Okay, so I will ask you for this part, maybe you print it and send me the PDF file, or we will decide some method later on. Okay, so make sure you are mentally prepared for this thing. Clear? Next thing is that you can do the same thing with the help of the built-in function in CV2. So this was to give you more idea, a clear idea how the things work. You can do also the same thing using the CV2. So remember, in the CV2 we have different types of functions because it's a computer vision library. So it has also got the Sobel Sobel operator to apply on the image to get the edges. So let's say this is the image we want to use as input. So this is the zebra, and here it is one important thing: how to use the CV2. So the function name is cv2.sobel. You can search it on Google. I told you many times, functions, what values they take, you will not remember these things. They are easily forgettable. So for that purpose, you search on the Google and you will easily know what is the required input parameter. So in this case, you provide first of all the image, clear? And then you provide the output format. What is the output you want? Okay, this is like a constant, you will not disturb it. Okay, we will discuss further about this. And the third thing is extremely important. Third thing says that it's the direction X or Y that you want to provide. Clear? What direction you want to do the derivative, X direction or the Y direction up. Okay, and the final one is the final input parameter is the kernel size. Remember, since many lectures we have discussed, if kernel is bigger, it means more filtering. So in this case, the filtering is not for blurring. In this case, the filtering is done for edge detection. So the bigger the kernel size, it means that it will be doing more rigorous or more strong edge detection. Okay. Over here till now we have only studied 3x3 kernel for edge detection. There can be bigger, but we don't study here in this course. Okay, so what can be the value for this direction? The direction parameter, you can provide it a value like two separate values. I don't know why they do like this. They should have done something, in my personal opinion, it should have been done inside the brackets, small brackets, parentheses, to show that this is one parameter. But they have kept it as two separate parameters. So here it is. This is your image in the Sobel operator. This is that constant we discussed. So it says that output format type. So output format over here is, so remember here, if you remember, I discussed earlier, what does it mean, this thing? When I told you that in CV2 there are many constants already given. Constants are only numbers. So they are given over there and they normally start with capital letters. So here is a constant and it starts with CV underscore 8U. It means that this constant is related to the CV command. So it is directly related to the CV library, not some functions. And what this constant do, it gives us the 8U. U means unsigned. Means that the output is 8-bit unsigned. And if you remember, 8-bit unsigned numbers are the numbers that range from 0 to 255. And this is the same range we have been studying since a very long time. And this also makes it clear that the output for the edge, it can be in other formats also. There can be many other formats. where you can have the number range in negatives and positive values, or it can be between 0 and 1. Many different possible ranges are there. Clear? Next is this thing that we discussed up, which is to specify you want the derivative done in x direction, then you will give 1 comma 0, or 0 comma 1, that is y direction. So two are given over here. Okay, and finally the kernel size, we give it over here the size as 3. So if you see, what it will do is that it will give us a result. This is the result x. So this is the result over here. Now it's up to you to decide. This is the image. Let's compare it with our image, what we did earlier. No, we didn't do it. So I suggest the zebra. You also do it with your own Sobel operator x, and check what happens. Let me do it quickly. So insert a cell over here. So I will put over here that this is Sobel using built-in function, and here I write Sobel. Remember, in your holidays, make sure you have these things, this setup installed. Do it, practice it at home. So this is Sobel using custom function. So custom means we make it. So Sobel is given just up to make sure. I will just copy it again to make sure that I don't have any messed up values. So let's say this is my Sobel X, done. So this is a 3 by 3 kernel, and I want to apply it on the image. So let's say I will just copy it to do it quickly. And it is this one, not this one, these three commands. I want to copy it at one place. So this one, I'll make changes. This one here, I will put it. So it is SX, not SY, small x. So instead of chess one, the image name in this case is zebra. So remember, what is the purpose? Why I'm doing this? I'm doing this because I want to see what is the difference in quality of my image and the image provided by them. So you see over here, maybe we need to make it a little larger. So here you will see how this fixed size command works. So it will make it bigger. Okay. Similarly, you can do this with this image. It's up to you. You can make subgraphs. No, 10 by 10 subgraphs to what happened. Okay, I did a blunder. You can make subgraphs or subplots to examine them side by side. And in these two images, I can clearly see that the image that is the edge result that is produced by the built-in function, it's more brighter. I don't know how they do this. It's more brighter and the lines are more thicker. Okay. Whereas in our case, it is a little bit dull image. But overall, if you see the results, they are almost same. I don't see that there are some extra edges that are detected which are not in my image. They are over there, but somehow they have enhanced those edges. But edges, they are at the same places. So they are present at same places wherever I detected. So that is it. You try to use both of them, the built-in and built-in CV2 function or the one created by you. They will behave in the same manner. Also, you have to do, remember, the Prewitt and the robots, you have to implement it. So this was your Sobel operator, and do it, and here you have got the Sobel operator that's working in the y direction. You see over here 0, 1. 0, 1 means that now it's working in the y direction. So if you see now, the image is very bright. These lines, they are not so bright now, but these are very, very clear now. Clear? The lines that come perpendicular when you are moving in the y direction, they are now very, very clear. Here they were dull or discontinued. Clear? So this is it. This is what we did over here. Now let's see the remaining theory. We want to finish this topic today. So we have seen this MATLAB, leave it. So we discussed, I think, this question in the class. It's better to compute gradients using convolution or correlation. So in the case of over here, when we see that we have symmetry, but there is a difference of signs. On one side there is a minus sign, on the other side there is a plus sign. So I would suggest that we should be using the correlation, because correlation does not flip the image. The difference between correlation and convolution is just like you flip the image 180 degrees and then you apply the correlation. That is the only difference. So instead of flipping, we use the correlation directly on the image. In the case of edge detection, because our filters, they are our kernels, maybe they are not symmetric, so it will not make any difference. Correlation, but convolution can make difference. Here is the example. If you see, we have discussed this. If your image, it contains noise, what will happen is that your output, because you are taking the derivatives they represent change, and even because of this noise, a little bit of noise, there is a lot of change over here in the signal, and that change is clearly that can be seen over here. Okay, be careful. So it means that always when we want to apply the edge detection algorithm on an image, make sure there is no noise. No, maybe noise which is very intrinsic. You cannot see it maybe, but it's inside the image, and that will destroy your results. So make sure that there is no noise. There is some sort of image filtering done before you apply the edge detection algorithm. Clear? So here were some of the results that we discussed. I think earlier we discussed when you increase the noise, the results become more bad. But in the case of lab, we have seen it that the noise does more harm than this. Okay. So let me show you one more example. I think I haven't shown you before. I don't know I have shown you or not. Edge, yeah. It comes next. It's not given here, but you can try over there maybe. So here for the same image, maybe just before the zebra example over here, maybe it should be put somewhere inside the lab notes. So here maybe I copy one of the complete. So the name is so let's make it a markdown. Sobel results on noisy image. Okay. Same X. So which noisy image I will be using? So this is my SX, and which noisy image I will be using, and let me choose it. So I have only this set of noisy images, so let's choose the salt and pepper noise. So Lena, salt and pepper. So here it is. Okay, so salt and pepper.png. Okay, so this is noisy image. If you want, we can display this image. Oh, sorry, remove one. So this is it, the noisy image. And now we copy the code for the result. And not this one. SX I have to apply because I put X over there. So name I will change it. Lena underscore noisy. Okay, and I will use the same image here, Lena underscore noisy. And if I want to see the result, so now you see the result. So you see the comparison. Here you have different image, chessboard, but you see clearly the results. But here you have a noisy Lena image and you are hardly seeing any edges, and this is a total disaster. So I suggest you to practice this with many other images. You will see that no approach for edge detection, either it's built in like cv2.sobel or cv2.canny, we will study in the future, or it is some kernel created by you, Sobel or Prewitt or robots. If the image is noisy, you will not get results, or you will get extremely bad results. Clear? So that's the theory. So first you have to smoothen the image. So smooth, you can do it with the kernel. So simple kernel or simple Gaussian kernel, it will make the image smooth and you can get the result. And I discussed this theory last time with much efforts. It will give you the result, which is the output will be a peak that represents an edge. So this is the peak. It shows that there is an edge over here that occurred in the image. Okay, but this peak is not enough because I told you the theory. The signal processing people or the communication people or the people from the electronics background, they know this very clearly that edge detection is a very painstaking job. It's not so easy. Through electronic hardware or through the circuits, it's not so easy to detect edges. And traditionally, even at the low level, when the people study computer architecture, they see over there that edge detection is much harder, whereas comparatively, the polarity detection is an easier job. So, what does it mean, polarity detection? We will discuss. So, here it was, your noisy image, this one. And derivative we take, so you see over here, we have the filter that's applied on the image, and we take the overall derivative that gives us the edge, a peak for the edge. So what we do is that instead of applying the derivative on the whole image, what we do is that we apply this derivative only on the filter. And I told you last time lots of advantages. If you apply the derivative on the whole image, first thing, it's too much time consuming. Image can be big. Image can have millions of pixels. So it will take too much time. Whereas the filter, you all know, it's a kernel. Its size is maybe 3 by 3, which is 9 pixels. Or it can be 5 by 5 or 7 by 7. So it's limited size, much smaller size. So applying the derivative on the kernel, it is same as it is applying on the whole image. So this equation is very, very important, very helpful in reducing the overall cost in this task. So here it is, we apply a derivative only on the kernel. So when we apply it, so this is our Gaussian. kernel, and when we apply the derivative, and I discussed last time in much details, that when we are going up the hill, that means we have some sort of positive derivative. It's just like the acceleration, or you can say that you rate of change. So when you are going up, you have a positive change, and that positive change reaches a peak value, and that positive change then decreases slowly until at the peak point your change becomes almost zero. Okay, because when you are going up, you slowly you reach to a zero value, and then there is a negative change that starts, and you continue until you finish it up. So this over here represents the derivative of the kernel, and when you use these two, this thing on the noisy image, it will give you the same peak. But this is the problem I was going to discuss, that detecting a peak value in circuits, in electronics, in communication, it's not so easy, it's not preferred. So for that purpose, we use the double derivatives. So what does double derivative do? We apply the second derivative on the first result. So this is the first derivative of h, and when we apply the second derivative, it gives us this result I discussed last time in full details, and this you can say this is the inverted Chinese hat. So this inverted Chinese hat, you use it. So this is the result of second derivative on the Gaussian operator, and this result you apply on the noisy image, it will give you a result that represents the edges by this pattern. Whenever there is an edge, there is a transition from high to low value, positive to negative, or from negative to positive. And these transitions are extremely easy in terms of hardware or communication, or even in terms of computers. It's easy to detect. I hope it's clear. We have done it in full detail last time. So which linearity property did we take advantage of during this operation over here? Did we take advantage of to first take the derivative of the kernel and then apply it here? So basically we are using over here the differentiation, and we are using association or not. So we are using differentiation property, I think, only. See. So this was it. We used derivatives for edge detection. So this is the theory. This is just the summary. So derivative theorem for convolution. This is a representation on the one dimension. So this saves us a lot of energy. So here you see the derivative that's applied. So if you are Gaussian, if you see it as a two-dimensional, what will happen is that if your single derivative, this is your original Gaussian. So remember, this was once an exam question. Gaussian, it is represented by, in a 3D shape, it's represented by a small mountain or small mound. Okay. The first derivative of this Gaussian, it's represented by this one valley and one mountain, a 3D shape. Clear? So why is it preferable to apply h to the smoothing function g and then apply the result to the image? So why it's preferable to apply h to the smoothing function g and then apply the result to the image? Why we are using combining everything together and then we do it to the image? Because what happens is that h itself, it's a smaller value, and when we apply the derivative on h, it will take less time. And first of all, we compute this smooth derivative operator and then we apply it. So once we do this calculation, derivative of the h, and then we apply it on the whole image, there are multiple advantages. One, it's easy to do. Second, which is I think more important, is that the f function F represents an image, and image, it changes every time there is a new image. You want to detect edges in different images, so every time there is a different image, there is a different F. Is it clear? So you want to do this calculation one time, this one, and you want to apply it on different images F. So it's B, option D, B and C both. So here are some details given. Leave these calculations. We are not interested. So here it is. If you see what happened. Here it is. If you see the derivative of the Gaussian filter in x direction derivative and the y direction derivative, if you see them, if you want to see them as an image, the image will be like this. Remember, in some time ago in one of the chapters we discussed that the Gaussian image, the Gaussian filter, if you look at it as an image, it's just like a white spot. So it's a circular white spot which is slowly fading when you go out from the center. Whereas the derivative of this Gaussian, the image of this derivative of Gaussian, it is this thing, black spot and white spot. This is x direction, and in y direction black spot comes below and then bright spot comes up. Clear? Here are some of the results. We are not interested in these codes, and here if you see, if you use smaller Gaussian, larger Gaussian, you will see different results. So these are the results for smoothing. So this is what we did many times ago in past chapters. So sigma, we always ignore this sigma, leave it. We don't discuss sigma. Next comes this called as the Canny edge detection. So we will go through this Canny edge detection, and what happens in the Canny edges. It's a new method. It was created by some PhD student. So there was a student enrolled in a PhD in computer vision, and during his PhD thesis he presented this idea about the Canny edge detection somewhere, and that became quite famous. He gave this algorithm. The results were so impressive that it became very quickly, as it was adopted, and it became part of the CV2 library. So remember the theory, same thing. Gradients, we use them to detect edges. And primary edge detection steps, what we do is that you use the smoothing derivatives. So you use the smoothing function in combination with the derivative to suppress the noise and then compute the gradient. So two things are together that are applied on the image. Okay, and then there is something called as thresholding. So thresholding means like a level, applying a level. So you apply a level. If some value is less than that level, you ignore it. So maybe, because remember these edges, they represent some brightness. So let's say if the brightness is less than 150, you will ignore it. If it is more than 150, you will select it. So that's like used to find out the region of significant gradient, where you see significant or important change. Then there is another step used called thinning, but we are not interested in those too much details. And finally, what they do is that they link the dots. So when we see dots, for example, there is I don't have. So let's say you have a pen. Let's say you have an image. There is one dot here. There is a gap. There is another dot. Another dot. So maybe if there is a little bit of, I am making it large, but maybe this gap is very small. So the image processing algorithm can connect them together. if the gap is too small. That is like linking, the linking step. Link or connect the edge pixels. So for this purpose, this Canny edge detection procedure is used. This is a function or algorithm, and that's quite famous in CV2. So it applies itself both the x and y gradients. You don't have to do anything for x and y separately. So here I will show you. And there is Canny. There is another one also. It's called Laplacian. So Laplacian filter is shown here. So there are many others, many, even many we will not study. So one of them here shown is Laplacian gradient operator. So it's given like this. So you see a one column. So this is one column 0 1 0 1 minus 4 1 and 0 1 0 again. So this kernel is given to you, and you can apply it on the image. And Laplacian you can also just like Sobel, you can directly apply it using the CV2. So you use the command cv2.laplacian, and again here you will only give two parameters, the image and the output, type of the output, which is over here cv underscore 8 unsigned. So it will give you this result, which is quite impressive. Okay. So the final one that we studied today is the Canny edge detection. So what you do is that in the Canny edge detection, the same steps that you saw in the slides, you denoise the image with a smoothing filter, and you find the intensity gradients just like you used Sobel and Laplacian. Here the intensity is found out for the edges. Thick edges, they are filtered to become slim. So for example, if there is a line which is very thick or wide with 3 pixel, it becomes a 1 pixel line. Okay. And then there is some thresholding to select the level of brightness, or to drop some pixels and to select others which are more important. And then you keep only continuous long lines for the final result. So how it works? It's very simple. Here it is for the Lena image, and you will see its results are the best as compared to all others. So for the Canny, what we do is that you use the CV2 Canny edge detection, which works for both horizontal and vertical edge detection at the same time. Clear? So the input format is like this, cv2.canny, and then you will give the source image, and you will give two numbers. One is minimum threshold and maximum threshold. What it does, you will see. Here it is. So you give image, you give the value 100 and for example 300. Okay. So it will give you result like this. And if your image has noise, what will happen? So in the case of noise, you will get this result, which is a disaster. Clear? You see over here, as compared to the above one, it is a disaster. You apply a median blur or any other filtering method on the same image, and this is the result of filtering. And now if you apply the Canny edge detection, now you will see some reasonable output. Clear? This was your Canny edge. So how it works? In the case of Canny, first you filter all these steps, they are implemented in cv2.canny. You filter the image with the derivative of Gaussian, and then what it does is that at the start of this topic we saw two things are there inside the edge detection: magnitude of the edge, how strong value it is, and then there is the direction or orientation of the gradient, which direction it has got. The formulas were given, but we don't discuss, or we don't go in those formula details. And then what happens is that if you have a line that is wide, lots of pixels, 3 pixels wide line, you reduce it to a single pixel width. This thing is also called as no maximum suppression. And finally, in the Canny edge detection, the final thing is you link the dots that you get at the end, you link them together. So you have got two thresholds. These are the two values that you see over there in the cv2.canny function. So one is the low threshold and the other is high. You use the high threshold to start the edge curves, and the low threshold is used to continue them. Okay, so what happens is that you give a value, for example 100. These are the typical values, and for example 300. Okay, so the edges, they will have value over there. That value you will compare with this. Okay, so you will start an edge if the pixel value, it's for example higher. Okay, depending on the values that are given over there, the system, maybe here I use 200. So depending on the values given here, the high threshold value, it will tell me that I start the line over here, this one, because the pixel value is 200. Okay, so I start it over here, I go over here, and in the future I will only continue to these pixels if the lower threshold value it satisfies. Okay, so if this pixel value is less than 100, maybe it's 50, I will not continue this edge. I will stop. And I will only start again in the future somewhere to make another edge line if the value is more than 200. Only then I will start again. Is it clear? So high threshold value, it's used to start the edge curve, and the low threshold value is used to if you want to continue. So remember, they are two separate limits for starting and continuing, because to start you are initiating a new edge, new line. Whereas when normally there is a line, sometimes it's very highly likely that line fades away somewhere. So you will give a benefit even if there is a small value, you will keep on continuing with that line. Clear? If it's not clear, ask me and I will explain it in your group also. So here is the original image for the Lena, and here is the magnitude of the gradient. This is the thresholding that's done. So in the thresholding we remove the pixels that are not up to over standard of values, and then they have done this no maximum suppression. If the line is too thick, that is not a good edge. Make it thinner. Okay, so these thick regions, we convert them into thin lines. So here it is in the Canny edge detection. When you want to detect the edge, so your thresholding, what it does is that it will only detect when the value of the pixel it becomes more than your threshold, which can be maybe, for example, 200. Leave this discussion on no maximal suppression. So here it is. You see, in the Canny edge detection, sometimes the pixels along this edge, they did not survive the thresholding. So for example, this was the picture of the Lena, and when we convert it into edges, many of the pixels, they are removed from here because of thresholding. So thresholding is important. Why we do it? Because if we don't use thresholding, there will be a lot of garbage pixels which do not represent edges. Remember, we are not interested in the whole picture. Picture is already there. We are only interested in the corners or in the lines on the outlines of the shape, the edges. So sometimes because of this thresholding, what happens is that even some valid points are gone. So here you see for the face, we have some points missing, some edges or some pixels missing from here. So for this, what we can do is that you can play with the thresholding values. So you apply a high threshold to detect strong edges. Keep it high. The more higher you keep it, you will detect only the strong edges. And then you link those strong edge pixels to form a strong edge with other pixels to make a strong line. And if you use a low value for the low threshold, you will detect weak but important. Plausible means important edge pixels. Okay, so it's up to you to play with these two values. If you keep the higher threshold value, the value you keep it high, then that will only detect strong edges. And if the low threshold value, if you keep it high, then you will be ignoring you will easily discontinue that line. So remember, if this is your pixel, this is your another pixel, now that makes an edge. Now if your lower limit of the threshold, it's high value, so maybe very quickly you will decide, no, this is not good value, I will not continue this line. So your lines will be shorter and broken if low threshold value in the Canny it's higher. For example, you select value Canny image, comma 150, comma 200. Now 150 is comparatively very high as compared to 200. So your image will have lots of small lines, small edges which are broken. If you want that your image should have continuous lines, lots of continuous lines, keep it small. Maybe make it 050 or 50. So keep the lower threshold value very small. So in that case, you can extend the strong edges to the weak edge areas. So here it is. If you are changing the lower limit, so here if you see there were no pixels. If you change lower edge limit, you will get over here some pixels. So it's up to you to play with these things. Here is some other thing, sigma, we will not be using. Leave this also. This is again scaling. This is a quiz. Canny edge operator is probably quite sensitive to the noise. True or false? So we all know it's true. It's highly sensitive for the noise. Noise destroys the result output of the Canny edge. Here it is. The recall, I don't think you, so we have already seen this. This is the double derivative, second derivative for the edge operator. And here it is the original Gaussian. This is original Gaussian smoothing filter, and this is the first derivative of the Gaussian smoothing filter. And what about the second derivative? Second derivative will be represented by this shape. This is like the Chinese hat shape, but in the inverted form. Here they have put it in the upright position. So here it is. This is the second derivative of your Gaussian filter. This is the one that we apply on the image so that it does not, even if there is noise, it will work on noisy images to find the edges. So this is MATLAB code. We don't discuss this. So hopefully this was the summary. Hopefully you have learned the filtering by convolution and correlation, and how to take derivatives by using those operators, and you compute the gradient. All these things we have seen over here that we use for edge detection. So we have discussed over here filters. We use them as templates, and we also we will go next and we will discuss some other things related to the edges. We have detected edges from the image. Now we will see how we can use it. Now let's go back and let's see Canny edge detection a little bit. So if you go to the labs, here it is. So these are the two threshold values. This is what I was discussing. So what changes it makes, for example. So this is your image. So if I put over here 300, no, the image is not correct. Load this image again. IMG. Okay, you have to go back, a lot back. This one, noisy image. IMG. So let me apply it on this base image. Okay, so this is the image. So here you see, in this case, the low and high threshold, I'm using 100 and 300. Okay. So remember, 300, the upper value of threshold, high threshold means that where should I start detecting the edge, strong edge. Okay. And the low value, it shows that where should I keep continuing the edges that I am working on. Okay, so if this value is high, then I will have lots of small edge lines in my picture. So here you see example, a lot of small lines, a lot of small lines. Okay, but if I make this much smaller, what will happen? Now much of it is connected together, much of it is connected, because now I am encouraging that whenever an edge starts, it should continue that line until the pixel has got this much value. Okay, but here I make 200, which means that only create a new edge when it is strong enough. So if I increase it more, you see, it will only start a new edge when it is very confident with this. So these are two values. uh, we cannot say that which one is good or bad. It's up to you. It depends on the use, what we want to do. But these two values, they can be used. They are like parameters. You can tune them for a different purpose. Clear? So this was it. One task I have given you to apply Prewitt and Roberts. The other task that is to detect the edge. Maybe this is the blood cell. So this is the season of maybe this one, or flowers, or so how it looks, this one. So this is the season of coronavirus. So this is some sort of blood cell. So if you can detect the edges on this using the Canny edge detection, and what you say, which parameters you will use for the lower and upper threshold values. Clear? So do this, and I will tell you later how you will submit these things to me. This ends our chapter on the edges, and the next one we will have will be how to detect lines in the images.